Welcome, everyone. On behalf of the CAOE, we are happy to have our North Carolina Pembroke group present their SRT presentation this morning or this afternoon, depending on where you are. Take it away.
All right. Our presentation and the survey we were working towards is called Towards Equitable Privacy Preserving Machine Learning Algorithms. Go introductions. This is our photo from our first day here. I'm Patrick Valente. I'm a rising senior at UNC Pembroke, so I'll be graduating in this upcoming spring. And I just transferred to Pembroke in the fall of 2022. This is my first internship, and first time this far out of this side of the country too.
I'm AJ Medina. I'm just a junior, and this is also my first internship.
My name is Selvarajah Mohanarajah, and I'm teaching at UNCP, University of North Carolina at Pembroke, and teaching computer science.
So this is what we're going to go over throughout the course of this presentation. We're going to do talk about why we're doing what we're doing, talk about the process of completing a survey, and we'll talk about both privacy and fairness separately and then together, and then we'll talk about the summary of our research and future directions of the other research.
Okay, I will start with that. So why we are doing this one, machine learning applications are everywhere, all the industries and all, right? So it is going to affect us. It is already affecting us. So we have to consider that carefully. And there are some concerns about machine learning applications. We are focusing on two of them, privacy and fairness. So about these privacy and fairness, Patrick and AJ will talk later, but just some introduction. So privacy in the sense,
I'll start later.
So machine learning application needs data. Sometimes people's individual sensitive data will be given to train the system, and after that, the models will not keep any information, but there are many instances privacy breaches. So, for example, this one is the image on the right is given to train a machine learning algorithm, but after 4 or 5 years, so that actually the machine learning algorithm should not keep those pixel data, so any coding, but they were able to retrieve at least some part of that, right? Not clear, but anyway. So similarly, there are many real instances, the medical records and other things are retrieved from a model. So model should not keep those things actually. They have to generalize and keep some weights, but so that breaches, so we are going to discuss about that later. And discriminations, the systems are also biased. We think that algorithms will not discriminate because they are just numbers and statements, and statements and so on. But really, that is not the case. This is one example. Compass. This one is used in the criminal justice system to predict whether someone will do some crime again. In this case, the system, both of them were captured when they stole a cycle. Actually, they borrowed without permission, and the system says that the person, the guy, the score is given, so 1 to 10. So he is given 3, and the other lady is given 8. So they have some criminal record, but this guy have more criminal records in the system, but still the system gave only 3. The other one get 8 high risk. But after 2 years, this guy is again in the prison, but that lady never did a crime. So this is a example, and they will explain later also. I will go here also. I don't know whether you can see that one. This is another example for bias. This I run only day before yesterday. So this is a BERT. This is like a chat GPT. That's a transformer bidirectional. So it will, the mask is there. It will complete that one. So Phoenix is a city in where, so that is giving the answers based on the trained information, trained based on Wikipedia and Toronto Book Corpus. So it says Arizona is the first choice. And the man works as something, so it says lawyer, carpenter, and that sort of thing. So I hide this one, and I'm sorry to give that. So this one is very bad, right? So this is the BERT recognized system is giving right the choices. So this is totally biased, but that based on the training data here, I think mostly because of this book was not Wikipedia. But this is a situation, right? So go back here. Where's that? So privacy, and we have to enhance those things on the system, but can we do that? We need to do both of that, right? So privacy and, can you move that? Okay. But the research shows that if you enhance privacy, that decrease the fairness, right? So that is the problem. So this is what we are trying to explore. How we can enhance both at the same time. The reverse direction researchers are on only one, we can see that. So this research, many show that. So enhancing privacy will increase bias in the system. Some of them say no, right? We will discuss that later.
Can we go to the next slide?
Yeah.
Where's the mouse? There it is.
That one, yeah. So why this is important for DHS? As people, security and safety is there, right? So the email systems will be used by many other entities, institution, and DHS will also use it, right? So the Homeland Security is right. They have to make sure that system is not discriminating against protected groups, and also revealing any any sensitive information, so that people will provide their information for the machine learning system, so that to train, right? Otherwise, people will be reluctant to give their data. So that need to be so make sure that systems are not discriminating and systems are not revealing, right? So privacy and fairness, and also at the meantime, they must be very effective, right? So they useful. Okay, so this research will be useful for that.
I guess you'll talk about this.
Okay, so when we first got here, we decided what our research phases were going to be, and the three main phases that we decided was a research phase, summarization phase, and the generalization/categorization phase. And Patrick and I worked together during the research phase, and we read through a lot of summaries and articles, and we began summarizing them in different sheets and categorizing them in if they were very relevant, not relevant, or sort of relevant to what our discussion was talking about. And this is the kind of summarization phase. And then the generalization phase is taking note of the technical details of each article. So we would look at the scope of the article. If it talked about black box, white box, or gray box, we would also see what kind of method they were using for privacy and fairness, if it was pre-processing, post-processing, or in-processing. And
As also, we talked about, because all these different articles normally had different ways in which they defined privacy and fairness. We also had to make note of that for future note too.
yeah, we would work with PhD graduates and decide if these articles had anything in common with how they describe privacy, how they describe fairness, and we would try and compare them and contrast them. For the categorization phase, we sorted every article like the relevant stages that I talked about.
And basically, in that phase was about fitting articles into more definitive categories so that we can make generalizations about the articles at large. And all this was done with the end goal of us being to produce a survey paper that we could eventually publish. First we're going to talk about some privacy threats in machine learning. And these are just common attacks that you see. First, there's what's called a member inference attack, which uses a model output probabilities and confidence scores to infer membership information, which can reveal sensitive information about individuals in the training set, which is basically, we're trying to see if an individual's data was used in the training of a model or not. That's basically what that is. Whereas a linkage attack combines an anonymized data set with outside information, and they look for overlaps so that they can identify specific individuals. And when we were reading for this paper, we read about how, I believe if you have access to or you have access to a data set that has an individual's date of birth, gender, and zip code, using public data, you can identify, I believe, something like 70% of Americans off of that information alone. And that's really what linkage attacks is all about, is combining different data sets in order to identify individuals. And lastly, we have what's called an attribute attack, wherein an attacker infers partial data from a public record data set, then uses the machine learning model as an API and identifies specific attributes of a person's private data. And I don't know if this is the next thing. Yeah. So as we were going about creating this survey paper, we did a lot of different visualizations and example programs. And this is one I wrote, where I wrote an example membership inference attack example, because this seems to be the most common that they talk about in the literature. So I kind of want to walk through how this works. So at the beginning of this, we're using what's called a library in Python called scikit-learn, and it has all these available data sets that you can use for training models. And a specific one, we're using a breast cancer data set. And in this specific data set, the Y column of the data set is just binary. It's 1 or 0, 1 meaning that a tumor would be malignant, and a 0 if it's benign. And the X is just all the other information that all the different information about the tumor, like its size, its shape, etc. Also information about the patient. And so what we do is we split this data set in half. And with the first half of the data set, as you can see, it's sort of around line 85-ish. We're just training a regular logistic regression model and fitting half of the data set to that. And then how the member inference attack works is we use, in this case, the second half of the data set, and we feed in the X values, and we get a prediction that the original model makes. And as you can see on the side of this model, if we compare it to what we know the actual output is, you can tell that it's about 95% accurate, the original model. But using those predictions and those X values together, we can train what's called an adversarial or a shadow model. And if we use this, we can feed in original X values, and we can predict whether or not that X value was used in the training of the original data set with about a 92% accuracy. And yeah, I don't think we have anything else to add.
Yeah, that's
all right.
Usually this one,
Oh, that's what I wanted to
generate
add.
synthetic data.
So usually when someone does this attack, they don't obviously have access to half of the data set they can use. They would use synthetic data, but to produce synthetic data, that's a very computational the computationally heavy task, which you usually have to have access to a GPU or several GPUs to do that. And you wouldn't just train one model, you would do it again and again to increase your accuracy. But we didn't have access to that technology during our time here. So for the sake of this visualization, I just split the data set in half and use the second half to produce the adversarial model.
Many of the, so when we first started, we wanted to find how to mitigate privacy threats. And many of the articles that we read proposed different techniques like K-anonymization, I-diversity, T-closeness, differential privacy, which is the most common one, and federated learning and more. K-anonymization is in a data set, at least K rows should have identical pseudo-identifiers.
So this can work, for instance, if you have a data set that has a bunch of date of births in it, you can use K-anonymization by removing everything but the birth year so that people can't be identified specifically based on their date of birth. And similarly, you have what's called L diversity, which says that for every set of rows with identical quasi-identifiers, there are at least L distinct values for each sensitive attribute, which is an extension of K-anonymization. How this could work is, for instance, if you had, say, a database about breast cancer tumors or something like that, and even if the date of birth was removed, you could still look at that plus other, you could look at the birth year plus other data, plus whether or not their tumor was malignant or not, and then perhaps you can use that to still identify people. So L diversity attempts to make that a little bit harder by having multiple people with the same quasi-identifiers.
And T closeness it distributes of a sensitive attribute in any equivalence class is close to the distribution of the attribute in the overall table.
So basically, as you could say, subgroups or minority groups should have a similar distribution that majority groups have to help mitigate privacy threats. So next we have we made a separate slide just about differential privacy because it is arguably probably the most important concept when you're talking about privacy in machine learning. It's a very popular tool that people use even to this day. And it works by injecting lab-based noise into given data, projected information. And we usually mathematically represent differential privacy using this equation. Basically what this equation is saying is that if you have two different data sets, which is D1 and D2, and you're feeding them into the same algorithm, which is your A, if these two data sets are neighbors, which is to say they differ by one element, so there's one, you can think of it as like one entry removed, the differential privacy says that these two data sets should produce identical outputs within a given, which is represented by an epsilon value. And
we also, this is mitigating privacy threats. Federated learning is the other one that we were also talking about, which models are training locally on one's own local data, so not as big as other aspects.
you're not also sharing your information with other people, which is the key aspect of it.
Yeah. Only the parameters of the produced models are shared via central server or P2P before then being distributed back to the others. Like a decentralized form of building models. It's very common in things like smartphones, smartwatches, and Internet of All Things devices.
Similarly, we have what's called multi-party computation, which allows multiple parties to compute functions together without needing to trust the other party with one's data, which can be combined with encryption for secure multi-party computation, which is called SMPC. I think the best example to show how this works is there used to be a problem called, I had it in the notes, but I can't see my notes, of course. There's I believe it's called the richest millionaire problem. It was a problem that was proposed in the 80s, which said, suppose there's two millionaires and they want to know who's the richest, but they don't want to disclose how much money they make to each other. how would they do so without exposing that information? And sort of from that, that's where the field of encryption and multi-party computation kind of arose. This idea of that people should be able to work together without compromising their data security with one another.
And then there's also homomorphic encryption, which it has clients encrypt that data locally, share it with the server performs computations on that encrypted data, returns encrypted output, which is then decrypted by the client. It's a higher computational overhead, particular with full HE. And then there's private aggregation of teacher assembles or page, which is students learn to predict an output chosen by noisy voting among all of the teachers and cannot directly access an individual teacher or the underlying data or parameters.
So the biggest thing when we were going into the survey is we wanted to first focus on just privacy, then just fairness, and then both of them together. And so with this slide, we want to talk about how, as Dr. Mohan alluded to earlier, about how there is this trade-off that you get when you pursue privacy, which is seen with a decrease in accuracy. So this is another visualization I made using the exact same breast cancer data set. In this visualization, we're first training the model with no differential privacy applied at all. And as you can see from the graph, it has an accuracy of about 96%, I believe, very high accuracy. And then we tested it at all these different epsilon values, where I think I generated 10 different models and we computed their accuracy and got an average. And as you can see, with if you start with the strictest privacy budget of an epsilon value of 0.01, your accuracy is pretty much halved to about 50%. But the trend you see is that while as your privacy budget gets more and more loose, your accuracy increases. Of course, you're losing privacy at that point, but a very, I would say, critical point of this research has been trying to find the ideal point for your epsilon value so you maximize privacy without losing too much utility. And so there is noise applied to this, so the results do change if you were to rerun this test again and again, but the general trend always remains that as you increase your privacy, or decrease your privacy budget rather, you see an accuracy which more closely matches the accuracy of the original model.
And so now we're talking about fairness, and we used two types of fairness, which was mainly what articles talked about, either group fairness or individual fairness, or they sometimes talked about both of them. Group fairness is equality between different protected groups.
Whereas individual fairness just says that similar individuals should experience similar outcomes. But in all the literature we read, group fairness is by far the most common. And so with the rest of the slide, I want to talk about it a bit more in depth. And to do so, I thought it would help to have this image on the slide, which is what's known as a confusion matrix. It's how we compare computed versus actual values, or expected values, I should say. Whereas if you have something that we predict to be true, and it's actually true, that's called a true positive. If it's predicted to be true, but it's false, false positive, and similar, we also have false negative and true negatives. So when you look at all these different methods for measuring group fairness, the most common is what's called statistical or demographic parity. And all it's just saying is that your y prime, which is the output, if it computes to a positive thing that is true, we'll say, that it should be the probability of that happening should be irrelevant depending on whether or not someone is part of a protected group, which is what is represented by that the A variable, which we can just basically as a whole, statistical or demographic parity aims to eliminate disparate impact. Kind of similarly, we have what's called equalized odds, which you'll see is exactly the same as statistic or demographic parity, except we have this extra y value, where this y variable is the actual, what the actual output of the model should be. And as you can see in this example, y can either be 0 or 1. So in this case, what we're doing is we're trying to equalize both the true positives as well as the false positive rates across different protected groups. And quite similarly, we have what's called equal opportunity, which most of you are probably familiar with already. It's a very similar notion to equalize odds, except in this case, we're solely focusing on true positive rates, making sure that they're equal between different protected groups.
The causes of bias in machine learning. There's two main sources of bias in machine learning, which is data bias and algorithmic bias. Data bias is data used to train the machine learning models and can be biased, even unintentionally. Why a fairness through unawareness blind approach doesn't really work, and models can still pick up on historical bias, which can influence decision-making, which is algorithm bias.
And Dr. Mohan already talked about this one in his introduction, but over here we have from an article which tested the Compass machine learning model, which predicts the recidivism likelihood of different criminals. And as you can see, it predicts that white defendants are at a much lower risk of recidivating compared to non-white defendants. Yeah, and similarly, I wanted to point out too, we're talking about this fairness through unawareness approach. That's basically to say, if we approach machine learning by ignoring whether or not someone is part of a protected group. And a good example of this is what happens in machine learning algorithms, which are used for the, which are used to approve loans for, say, houses or for business loans or whatever. These are often processed using machine learning algorithms. And as you may know, historically in the past, certain groups were legally able to be denied access to loans. And even though that process isn't in practice anymore, the effects of that continue to persist. And so when you're training these loan models on historical data, there's a chance that, for instance, even if you ignore someone's race, the model could pick up, for instance, that it should deny loans to people who live in certain zip codes, for instance, which is where your algorithmic bias comes in, where it's picking up on that historical segregation that existed and using that to still disparately impact certain individuals today.
So talking about mitigating bias in machine learning this time, mitigating through privacy, remember that machine learning algorithms can learn hidden patterns. So
basically, privacy alone isn't enough to mitigate this data, as we just talked about. You can't just hide whether or not someone's part of a protected group and expect that alone to to solve your problems.
Yeah, computers are a lot smarter than humans, so they can find things that we can't really see. So it's easy for them to
pick up on that.
Pick up on private matters. Maybe through group equality, this is using things like fairness, like as talked about before, statistical parity, and mitigating through awareness is individual fairness by treating similar people similarly. And then there's algorithms for this, which are pre, post, or end processing methods, which is what we try to look for in the different articles.
Okay, now, so we have that privacy issues and fairness issues, but we want to overcome that and improve, enhance both. So first, 2013 actually. So this privacy separately, fairness separately, the long history of research, 25 years, but the first time that paper talk about that is a DHS funded research actually. So talk about that privacy alone. They are the one DP, differential privacy. They define that, and also they define that individual fairness also, fairness through fairness. So, so they first indicated that this should be we have to treat them separately. And after a long time, so 2018, 2019 actually, many papers started coming. So they are trying to put them together, discuss about privacy and fairness, interconnection, and enhancing them together, and so on. So privacy is about safeguarding past data. Fairness is about treating people in the future. So, but why they are conflicting? Because they both are in the same ML life cycle. Because when you treat them, I will talk in the next slide. So, so I will go to the next slide. Okay. So privacy attacks actually mainly black box because they don't have the model algorithm or training data, so they only have the model, and they have to give the input and get the prediction, and based on that they are trying to get the training data at the end of it, right? So this is very hard, but this Patrick explained that member inference attack is very cool method, and they try to get that information here from the training data using the only prediction here, right? And the bias, actually here we discuss about this one. The model is there, but we are giving the future data or present data and try to give unbiased result. So input, this is also we good only black box type, right? So you give the input and get the prediction, but it should be not be biased, right? So that's the idea. So what they are doing is privacy protection and bias mitigation. Privacy protection, they put the noise, the DP, differential privacy. Actually, there are 4 different areas they put the noise. One is the input data. They introduce noise based on Laplace mostly. And objective function, so like DP, SGD. So that functions, they put the noise, they are clipping, and so there are different technologies they use, right? So, and also PATE, AJ discussed about PATE, so that also in under that model building algorithm state. So they add noises, the noise are random noise, right? So if there's a data 5, they just put a random number, 1.5 or something like that, or subtract it, or maybe 5.5 and 4.5. Instead of 5, they use the right? They 5.5 or 4. So at random noise, they are in different places. And output perturbation, they are outside. When the result comes after the result, also they can add some noise so that the privacy is preserved, right? So mathematically they proved it, right? The DP will work on that, right? Based on the Laplace and Gaussian distribution. So post processing is after you get the noisy output, and try to minimize the unwanted noise or standardize, right? Sometimes this may go minus, right? Number of children, so it may give minus data because the noise is added there. So they have to do something, right, to make it useful. So that is post processing, right? In the bias mitigation, they do the training data pre-processing. That means if there are many male software engineers, they just change the male to female. So that is planned, right? Not random. So they are changing the training data, right, in the privacy preservation and also bias mitigation. But there, that random noise is added. Here, planned changes are added, right? So why they are conflicting? So that is a problem we have to analyze, right? So why that is conflicting? And can we enhance both of them together in this, right? Okay, so there are many researchers. We went, so AJ and Patrick and me went through many papers, right? So some papers say, some research say that, yeah, we can do that both, right, at the same time. Some says no. So that the papers we went through, some of them says that, we cannot enhance both at the same time, simultaneously. So the first paper, some of them are theoretical, just proving, there's both of them, both of the DP and this fairness metrics are probability based, so mathematical, so they can prove D work of that. I don't know the pronunciation, maybe D work. So they said that it can be done both, right? But mainly individual fairness. And this Cummings et al. They said no, right? So they proved in theoretically that the pure DP, EDP, and pure fairness cannot be achieved. But they have packed learner. That's a new concept here. Based on the DP, they enhance something on top of that, probably accurate. So the learning on that, so they add something on that, right? So that can be done. So that is their research. And there are many empirical studies. They say that they prove that it is not possible. When they increase, that it comes down, right? When mainly they did the one way, so they increased privacy and fairness comes down, right? So they saw that in 5 or 6, this guy, this research, they created 5 models and show that everything for every model that happens. So, and the last one is actually only one. We found that in the reverse direction, they try to increase the fairness and see that privacy is going down. That is, there are many papers about only, not many actually. This after 2019, we found around 20 papers, and we have checked about 15. So what we need to do next, right? So that's the final thing. So this is a relatively new discipline on after 2019, or many papers. Most of them are dealing with classification, binary classification. 1 or 2, they were dealing with clustering and generative models, language models, and reinforcement models. And most of the papers are only talking about DP. Some there are federated learning. There are some and packed learning also, one paper. And mostly they are talking about equalized dots, right? So equalized dots is almost same as Patrick told, that statistical parity. Only here their training set, they also consider the Y value, right? Actual value. And equalized odds is the main thing, the main metric the researchers use. And we need to explore more combinations, different combinations in this area. And often analyze in one direction, as I said earlier, privacy, how privacy protects when we enhance privacy, how fairness will be affected, not in the reverse direction. Only one paper found that, Chang's paper. So, so this area also we have to analyze more. And another thing is it feasible to attack? So that I haven't seen any paper that. So that means if an adversary, can they attack the system and get advantage, unlawful or unethical advantage, right? So normal system, the college admission and those system, people are taking those advantages, right? So can the machine learning system, can we attack that and get some advantage, and how we can protect that? So that sort of analysis we can do that. So that is our future direction. And
we just had an acknowledgement at the end as Amy had already introduced the I don't know, you'd say they're both postdoctoral, and I believe Yushuan is still a doctoral student. But these three students, along with Dr. Ross, worked with us a lot to give us guidelines and goals and milestones to work throughout the project to keep us going throughout the process. We also want to give special thanks not only again to Dr. Ross, but also to Dr. Escobedo, Amy, and Casey because they did a lot of work to help welcome us in and get us settled here and support us throughout the 10 weeks that we're here. I also want to thank ORISE, ASU, the CAOE, and the DHS for allowing us to even do this research in the first place.
thank you very much for all of you. Questions? Any questions?
Work paper says you need to consider fairness and privacy separately. After doing all this review, do you agree with that conclusion?
Not yet. There are two things we have to analyze further. So some of the papers say that we can do it. Some of them say no. But empirical analysis, most of them say no. So the theoretical only, right? I found that they said yes, we can do that, right? But empirical, so one paper they did, so except that most of them, no. So that we have to analyze further, I think, so we can come to a conclusion now.
Yeah, well, we've already talked about this, you, of course, but for the people on the call, that a lot of papers, there's a very heavy emphasis in the literature on either doing privacy and accuracy or fairness and accuracy, whereas there's a very few that look at the two like intricately together. As Dr. Mohan briefly mentioned, that there's only a handful that talk about them together. Yeah, so it's hard to say right now, I would say. As Dr. Mohan pointed out, there's one article, I think it's on here.
Check the last one.
That was another one I was thinking about. Oh yeah, so the comments that all talked about, I would say what's a commonly held belief in this sort of sphere is what's called the impossibility theorem, which is to say that, yeah, fairness and privacy cannot coexist at the same time. Obviously, there's a lot of research going on right now to sort of debunk that, but that's sort of, I feel like, in a lot of the literature, that's sort of the presumed belief going into whatever research they're doing. Any other questions?
Thanks, everybody. Great job.
Thank you all. Great job.